Hey YouTube, in this video I want to talk a little bit about what happens when you run your code. So my motivation for making this is basically just the fact that coding has gotten so popular over the past couple of years, but computer engineering and computer architecture haven't really gotten as proportionally popular. And I found that there are a lot of developers who really know what they're doing or they're getting into development, but they don't have as good of an understanding of what's going on under the hood. So today we'll be working with C. And if you don't use C or you don't have a C compiler, the one you're looking at here is probably the most common and the easiest to install. So go ahead to gcc.new.org and download the C and C++ compiler if you don't have it already. You may have it. One easy way to test is to just go to your terminal and do something like gcc-v, and you'll either get some version information or you'll get your terminal telling you that it doesn't recognize this command. So go ahead and install GCC if you haven't already, and you can see if you can run some basic C code. So I'm going to have some code in this video, but all the code is really simple, and especially the assembly code we go into might not work on other devices. So I'm not really going to have anything on GitHub for this, but the code will be really simple, so it shouldn't be too hard for you to type this out on your own. But this is basically just a counter running up to 100 and then printing out its value. So it should be printing out 100. So if you wanted to just run this C code, you could do something like gcc-o, we'll call it just count 100, and we'll be running it on count100.c. So -o count 100, this is basically the name of the executable file we'll be generating. So you run it, you see the file gets generated. So you run the executable, and it prints out 100, just like our program expects it would. But this isn't really what we're interested in today's video. We're more concerned with the intermediate step, which is what happens between the C code and the executable, and that's the assembly. So what we're going to do instead is we're going to use the -s, capital S tag here. So gcc-s on our C file. And you'll see that will generate count100.s, and that is an assembly file. So we can open it up and look at it, and this is basically the assembly code that was generated based on the C code that we wrote. So if you're not too familiar with assembly, this might be pretty hard to read, but if you're somewhat familiar, even if you don't know x86-64, which is the architecture you're looking at right now, most assembly languages are pretty similar. So you can kind of get a good idea of what's going on. But if you know absolutely nothing, the basic idea with assembly is that this left column here, these are instructions. So things like moving data, comparing data, jump. This is probably something like jump on greater than, comparing to, and deciding whether you're going to keep going or you're going to jump to another line. This is something like addition, another jump, exclusive or. You get the idea. These are all different instructions, and then next to them are basically just two operands, I guess you would say, that the instructions are performed on, and then the data lands in essentially a register, which is basically just a place where data can exist. And usually things like this are probably registers, like this is probably a register, this is probably a register, so on and so forth. So basically all the code that you write here, your compiler is going to run through it, and it's going to generate some instructions that are pretty close to being one-to-one with what your processor is actually executing. So this is sort of the most human readable version we can get of machine code before it actually just being zeros and ones. So you don't have to fully understand what's going on here, but just recognize that this is at least an intermediate step that we can now run the code of. So we've used our C code to generate the assembly, and likewise we can run our assembly code. So we'll use that same output file name, so that will modify our executable using our assembly. So we're now generating the executable based on our assembly, and we can run it again, and of course the result will be the same, because this assembly is just doing the machine code version of what our C code was doing. And to just sort of show a simple use case of that, even if you don't know exactly what this is doing, you could probably scan through this file and recognize, like, hey, this is the only hard-coded 100 in the file. That's what we're using to count up to here. So you could probably, just as a test, do something like 200, save this file, and now let's generate the executable again. So once again, we're going to compile our assembly file into the executable, and we're not even going to touch the C file. So remember, our C file still says we're going to do 100, but we changed our assembly file to say, hey, we're actually going to 200, and we can prove that that happened by running our executable again, and now we can see that our printed out value is 200. So the idea here is you could basically write or modify or do anything with your assembly code here, and now you have the capability of running it directly, and you can see the result. So I'm not super familiar with x86 64 architecture. I mean, I know other assembly language, so I have a pretty good idea of what's going on here. But if you didn't want to guess and you actually wanted to sort of learn how to program in this language, you can take a look at some of the documentation here. So here are some of the instruction listings. So it gives you some instructions, like for example, add. This is literally adding two numbers, logical and. You get the idea. This is the instruction list. And over here, you could even see things like the opcode, which these are literally the zeros and ones that are going into the control on your processor, telling it what kind of instruction is being performed. And this is pretty heavy. I wouldn't suggest that anybody dive right into this as a first assembly language, but it is good to know that the information is here in case you need it. If you wanted a simple comparison point, because this is pretty heavy, just to see what part of this is sort of boilerplate and what part of it is actually a result of the code you're running. A good example I have here is just this barebones.c. This is literally just a main function that returns 0. Just to quickly show you what this would look like if I tried to run it. So let me do something like gcc-o, call this barebones, and we'll run it on barebones.c. We need to use the other command. We want to generate our assembly. Yeah, here we go. So instead of generating our assembly on our count function, we want to use our barebones.c. So let's take a look at this. And if we just go like side by side on these, you can see that all this data at the top, as I change between these files, you'll probably notice that most of this isn't changing. Like things like I'm using Mac OS, and you get it. Our main function declaration. It's really, I guess, probably this line is the first one that's different. Yeah. So pretty much everything above that, this is all just boilerplate. And then even below, like for example, moving this 0 into this register and then popping and returning, this is probably the same thing that's happening at the end of this, I would imagine. Or maybe not. Oh, well, similar, but not quite. Maybe I don't understand that well enough. But you get the idea. Just even the most bare bones C file that you could use here still generates a good amount of boilerplate. But at least here you could probably recognize things like, okay, these are some points that you're jumping to, function declaration, and a good final point to sort of bring this home. I'd want to use something like a factorial function just because of its simple use of recursion. So you can basically write a factorial function that if it's 0, the factorial of 0 is 1. Otherwise, it's going to be the number itself times the factorial of 1 below it. So it illustrates a pretty good example of recursion. If you were just curious, how does a loop work? How do if statements work? The different branching and jumping. I think this is pretty instructional. So let me generate the assembly for this. So yeah, here you can see this is the assembly. And you could basically go through and figure out, when is it doing the jumping? What do these declarations actually result in? And where does the data need to land in order for it to actually be used in our main function? Lastly, I basically just want to reiterate that it's good to know that the x86 instruction list is here, but it's probably not a good starting assembly language to learn. If I just scroll through this a little bit, you'll see it's really dense and it's a lot to get through. But one that's much easier is called MIPS. It's basically an architecture that I think was even designed to be mostly educational, but it's really, really simple, pretty watered down. So like if I go here, you can see it's just things like add, subtract, your logical operators. It's much simpler, and more importantly, it's a whole lot simpler to get down to the zeros and ones. Like the encoding is really, really simple to get down to. So you can figure out exactly what bits are being fed into the processor, which is sort of like the whole end game of this. So you could view exactly what it would look like. So for example, here's what a MIPS processor might look like. And this is where the instructions live. They basically come out, they get divided up, based on what their bits represent, and they tell the processor what kind of instruction is being performed. And there are components that will do math and components that will, control other things. Most importantly, the program counter will say what line of the instruction we're pointing at. So when you make decisions and such, like branching or jumping, you're basically telling the program counter to point at a different line. So if you really wanted to sort of get into what's happening at the actual hardware level, studying something like MIPS or ARM would be a really easy way to get a good idea of it. And then once you have that foundation, you could sort of dive into something like x86. So that's it for the video. Hopefully you guys were able to get a good understanding of what's going on here. And if you have any questions, feel free to ask it in the comment section. So if you like the video, drop a like. And if you want to see more content like this in the future, consider subscribing. Thanks again.